In the first part of this series on the framing of decks and balconies, we explored the essential role of guardrail systems in protecting occupants from the risk of falling off elevated residential decks. We began by framing the appeal of elevated decks, including their unique ability to extend living space, connect residents with the outdoors, and enhance the architectural character of a home. But we also acknowledged the very real hazards they introduce when not properly engineered, especially at the perimeter, where guardrail failure can have catastrophic consequences. That discussion highlighted a critical, often overlooked truth: guardrails are not decorative afterthoughts. They are structural safety systems that must be designed to resist real and sometimes sudden loads. We focused specifically on guardrail anchorage, where the system is attached to the side of the framing at the perimeter of a deck. This is a common configuration that, when properly detailed, offers robust resistance to outward and lateral forces. In the second part of this series, we turn our attention to a different but equally important configuration that consists of guardrail systems that are anchored at the top of the deck framing. This setup is also frequently seen in residential construction, although the structural elements are sometimes covered with architectural finishing. While it may appear straightforward, the top-mounted approach introduces its own set of structural challenges, detailing considerations, and code compliance issues. This continuation builds on the foundational understanding established in the first part of this series. However, it stands on its own for those interested in appreciating its unique features. Whether you're a builder, designer, inspector, or homeowner, understanding how a top-mounted guard system functions and the important considerations in its design is essential to ensuring both code compliance and life safety. Let us now examine the structural principles behind top-mounted guard anchorage. We will consider a steel guard post with a base plate welded at the base. The base plate is a 6-inch wide square base plate that is pre-drilled with 4 holes spaced at 4 inches on center as shown. The thickness of the base plate should be designed by checking against the moment demand at the bottom of the post. The height from the top of the guardrail to the top surface of the deck is 42 inches. The deck has 2x6 decking planks whose actual thickness is 1.5 inches, just like the previous example. Since the guard post is attached to the framing below the decking, the moment arm will be 42 inches plus 1.5 inches, which is 43.5 inches. Before looking at the forces in the anchorage, let us briefly describe the approach for the design of the post and the base plate, as well as the weld connection between the steel tube and the base plate. First, the moment at the base of the base plate is the product of the length of the post and the lateral force at the top. We have shown that the distance from the top of the post to the bottom of the base plate is 43.5 inches. Therefore, the moment is 200 pounds times 43.5 inches, which is 8,700 pound-inches. This moment is acting at the base plate along with the 200-pound shear force, which is constant along the post all the way to the base. The design engineer needs to design the post and the weld connection between the post and the base plate to support both the moment and shear force. Additionally, the base plate must be designed to support the moment that we have determined. We have determined that the moment at the base plate is 8,700 pound-inches. The guard post and base plate wants to rotate outwards. This rotation is resisted by the lag screws or bolts that are provided on the interior side of the base plate. If the base plate is very rigid, all the screws or bolts will resist the overturning moment as the base plate attempts to rotate about the outer edge. However, to simplify the analysis, we can assume that the only fasteners in tension are those along the interior edge. The moment arm of the resisting moment will extend from this line of lag screws to the center of compression on the other side. If the base plate is adequately designed against bending or deformation due to the moment at the base of the post, we can conservatively assume that the center of compression will occur at the center of the lag screws along the edge experiencing compression. Since the holes are spaced at 4 inches, the moment arm is therefore 4 inches. Going back to the equilibrium equation, we can say that the loading moment is equal to the resisting moment, Since we know the loading moment and the moment arm, we can determine the tensile force in the fasteners. Therefore, the tensile force at the fasteners resisting the uplift will be the quotient of 8,700 pound-inches and 4 inches, which is 2,175 pounds. Since there are 2 screws or bolts resisting the tensile force, the force at each fastener will be 1,088 pounds. Having determined the demand forces, the next step is to select the appropriate connectors and to determine the capacity. Let us assume we are using lag screws in this example. The withdrawal capacities of lag screws are provided in Table 12.2a of the NDS. These are provided per inch of embedment, which means that the capacity depends on the length of embedment into the main member, which is the wood framing supporting the guard post. When deciding on the diameter and embedment, the designer also needs to keep in mind that the tabulated values are not the final capacity. The capacity determined from Table 12.2a needs to be multiplied by applicable adjustment factors. Adjustment factors that are less than 1.0 will decrease the design capacity of the lag screws or connectors used. On the other hand, adjustment factors that are greater than 1.0 will increase the design capacity. The applicable adjustment factors are provided in Table 11.3.1 of the NDS. The design capacity of fasteners used in lumber framing depends on the characteristics of the lumber material that it penetrates as much as it depends on its own material capacity. Adjustment factors are used to modify the capacity of connections to reflect the effects of the local ambient conditions on the characteristics of the lumber element and the connection as a whole. According to Table 11.3.1, for withdrawal loads and considering allowable stress design, the applicable adjustment factors include the load duration factor, the wet service factor, the temperature factor, the end grain factor, and the toe nail factor. If we assume normal temperatures, the temperature factor defaults to 1.0. The end grain factor and toe nail factor do not apply because we do not have end grain connections or toe nail conditions. Therefore, these two factors will also default to 1.0. We are left with the load duration factor and the wet service factor. The load duration factor is covered in Section 11.3.2 and Section 2.3.2 of the NDS. This factor captures the fact that wood has the property of carrying substantially greater maximum loads for short durations than for long durations of loading. When it comes to the design of wood guard posts, there is ongoing debate within the engineering community regarding the appropriate value of the load duration factor. Wood elements designed for short-term loads such as wind and seismic loads are permitted to use a load duration factor of 1.6, while typical live loads have a load duration factor of 1.0. Many practitioners apply a factor of 1.6 in the design of guard posts, citing the short-term, incidental nature of the 200-pound load specified by the IBC. Others advocate for the more conservative value of 1.0, arguing that this is a live load and should therefore use a load duration factor of 1.0. Please see the link in the description to a publication by the American Wood Council titled The Prescriptive Residential Wood Deck Construction Guide, where a load duration factor of 1.6 is advocated on page C11 on the basis that the guard post would not see the 200-pound outward load for more than 10 minutes cumulatively in its lifetime. Additionally, please see the links in the description to engineering forums where this question is the subject of discussions by professionals in the industry. The other adjustment factor is the wet service factor. The wet service factor is tabulated in the NDS supplement at the section on Table 4A Adjustment Factors. The wet service factor, which is denoted as CM, adjusts allowable stresses to account for the effects of moisture when the wood member is used in a high moisture environment. According to the National Design Specification, the wet service factor adjusts the reference design values when moisture content in the wood member is expected to exceed 19% for an extended period of time during service. According to Chapter 4 of the Wood Handbook, which is freely accessible from the Forest Product Laboratory website, wood is a hygroscopic material, which means that it absorbs moisture from the surrounding environment. The NDS in Table 11.3.3 requires the use of a 0.7 factor for lag screws used with lumber whose in-service moisture content will exceed 19%. For cases where lumber is not protected from contact with moisture from rain or other sources, the 0.7 factor should be used. This will reduce the tabulated capacity by 30%. After designing against withdrawal, the fasteners also need to be designed against shear. Since the total shear is 200 pounds, the shear at each of the 4 fasteners will be 50 pounds. Therefore, the designer needs to ensure that the lag screws can resist this loading. Given the large difference in magnitude between the shear force and the tensile force, we can see that the sizing of the screws used will largely depend on the tensile demand than the shear force. So far, we have been concerned with the transfer of the loading from the guard post and base plate to the deck framing. The next item that a designer needs to consider is whether the framing elements that are receiving loading from the base plate are adequately supported to prevent rotation or rolling over. The deck edge shown has a deck beam at the edge. The floor joists are framing perpendicular to the deck edge and are supported by the beam. Since the beam is not wide enough to support the base plate at the guard post, blocking is added right next to the beam. If the beam is nominal 4 inches wide and the base plate is 6 inches wide, we can provide another 4 inches wide blocking spanning between the deck joists. If we apply the 200-pound force at the top of the guard post, base plate and the edge member will want to pull away from the deck and rotate outwards. To prevent this from happening, 1 or 2 anchor devices may be provided as shown to hold the beam back to the deck. If we look at this connection from above, which is also known as plan view, the connection we have described shows joists supported by the edge beam with blocking provided between the joists right next to the beam. The base plate is placed above the beam and blocking while the anchor device is placed on the outside face of the joists. In this case, 2 anchor devices are shown. Note that the blocking is supported to the joists by shear clips on both ends as shown, or may also be supported by end nailing through the joist. The shear clips or nails or screws supporting the blocking must have sufficient capacity to support the vertical loading from the guard post. Please recall that guard posts must also be supported against a 200-pound vertical load in addition to the lateral load that we are considering. This configuration is by no means the only way to prevent edge framing supporting the top-mounted guard post from rolling over. There are many framing configurations that may be used by a design engineer to prevent out-of-plane rotation at the beam. The 2024 IRC also provides prescriptive framing requirements to prevent rolling over of the edge framing members, and we will highlight the code section shortly. Therefore, the framing configuration in this example is only demonstrating how one configuration functions to prevent rolling over due to loading from a top-mounted guard post. Let us now introduce some numbers so that we can have a feel of the magnitude of loads that we are talking about. First, we will assume that the deck beam is a 4x10 member supporting 2x10 deck joists. This means that the actual depth of both the beams and joists is 9.25 inches. Since the beam and blocking want to rotate outwards due to the lateral force at the top of the deck, we can assume that the point of rotation is at the base of the beam and deck joists. However, we discussed in the previous video that the center of rotation is also the center of compression, which we can assume will be along line B, which is 2 inches above the base. Raising this point 2 inches above the base will reduce the resisting moment arm and therefore increase the force at the anchor device. Additionally, by placing the center of compression 2 inches above the base, we have enough material above and below this point to provide resistance against compression. Please see our discussion in the previous video on side-mounted guard posts. If we consider the height of the guard post, which is 42 inches, the height of the decking, which is 1.5 inches, and the depth of line B from the top of the beam, the total distance from line A to line B is 50.75 inches. Therefore, the applied moment will be 50.75 inches times 200 pounds, which is 10,150 pound-inches. This is the moment that wants to rotate the beam away from the deck based on the center of rotation that we have selected. The resisting moment arm is the distance between the location of the anchor device and the center of rotation. In this case, the distance is 5.25 inches. Therefore, the resisting moment is the product of the force in the anchor and the moment arm. Since the applied moment is equal to the resisting moment, the force in the anchor will be 10,150 divided by 5.25 inches. The force is 1,933 pounds. The anchor must have sufficient capacity to resist this force. If 2 anchors are provided, then each anchor should be able to resist half the force. In conclusion, we can see that framing members supporting guard connections must be adequately braced to prevent rotation. The 2024 IRC has introduced a new section that provides prescriptive requirements for bracing of floor framing members supporting guards against rolling over. These requirements are covered in Section R 502.11.3 under the title Roll Bracing. Please leave a comment below if you'd like us to do a video about the roll bracing provisions in the 2024 IRC. Just like we did in the previous video on side-mounted guard posts, let us discuss the corrosion protection requirements. In most cases, decks constructed using exposed sawn lumber need to be preservative treated. Some preservative treatments are highly corrosive to steel, especially in wet conditions. Therefore, Table R 507.2.3 of the International Residential Code specifies that connectors and fasteners used in deck construction must be coated for protection against corrosion. For nails, the code requires hot-dipped galvanized nails per ASTM A153 Class D or ASTM A641 Class 3S for fasteners not exceeding 3/8 inch diameter. Stainless steel, silicone, bronze, or copper alternative finishes are also permitted. For bolts and lag screws, the code requires hot-dipped galvanized bolts and lag screws per ASTM A153 or mechanically galvanized steel. Stainless steel, silicone, bronze, or copper alternative finishes are also permitted. For metal connectors, the code requires ASTM A653 type G185 zinc-coated galvanized steel. Other requirements and alternatives are provided on Table R 507.2.3 of the International Residential Code. What do you think are other considerations that must be kept in mind when designing and constructing the anchorage connections at the base of guard posts? Please leave your comments in the description. If you enjoyed this video, don't forget to give it a thumbs up and subscribe to the channel, and do not forget to hit the notification bell so you never miss an update. Your support helps us keep creating great content, and we'd love to have you join the community. Thank you for watching.